So let V be a vector space over a field K, and we are going to pick V1, V2, etc. Vm, all vectors in the vector space V. And let us say we have a vector W, and vector W is equal to A1 times V1 plus A2 times V2 plus etc. plus AM times Vm, where all these AIs are in the field. So A is a scalar, A2 is a scalar, AM is a scalar, and those V's, they are all vectors, okay? They are these vectors here, V1, V2, Vm. So if a vector W is equal to A1 times V1 plus A2 times V2, etc. plus AM times Vm, we say that W is a linear combination of V1, V2, etc. Vm. So this is a very important concept that we are going to use now in this chapter of linear combinations and linear spans. Now let us say we have a set S, and that set S is a subset of V, a vector space. We introduce now the concept of linear span of S. So what is, well, span of S you can write this way or this way. So if S is the empty set, then the span of S will be the singleton, the set with the single element 0. If S is not the empty set, then the span of S will be all the linear combinations of vectors in S. Okay, let us jump to one example. Let us say we have a vector U in R3. Question: what is the span of U? So what is the space generated by this vector U? A vector in R3. Okay, so that will be a vector with components U1, U2, U3. Okay, and this component is in the field, of course. Okay, so what is the span of U? The span of U will be, so we have vector U here from the origin, of course, and the span of U will be this, I'm going to call it R, a line that crosses 2 points, this point where the vector takes and the origin. So one vector in R3, the span, or one vector in R3 spans, the space that it spans is a line. Okay, another example. Let us pick vector U and V in R3, where U and V are not the zero vector, and they are not a linear combination. Okay? So, question, what is the span of UV? So, what kind of space vectors U and V span? So U and V will be spanning vectors in the form A times U plus B times V, where A and B are in the field of the reals. Okay? Okay, so geometrically, what is this? So geometrically, the span of U and V will be a plane in R3. Let's call it plane alpha. So the span of U and V is the plane in R3 through the origin, of course, and the point U and V here. Okay, and then you'll get a plane alpha. That's the span of U, V. Okay, now I'm leaving here a theorem without proof. So let us say we have S, a subset of a vector space V. 1. The set span, so the space spanned by S, will always be a subspace of V, and this subspace will contain S, the set itself. 2. If W is any subspace of V containing S, then the span of S will be in W. So this means if we have a vector space V and W is a subspace of V and W contains S, then the space spanned by S will be here. So not only S, the set S, is a subset of W, but the space generated spanned by S will also be in W.